Good evening, everyone.
Good evening.
So today we are going to study about code division multiple access, and we'll solve some of the questions based on the week 5th lecture. Just wait for 2 minutes. My pencil is discharged. So today we are going to study about CDMA. CDMA stands for code division multiple access. So basically, it is the basis for most of the advanced third generation cellular standard, such as WCDMA, HSDPA, HSUPA, and CDMA 2000. So this is the basis of these third generation wireless standards. So the need of CDMA is for the multiple access. Like let's suppose multiple users are sharing the same channel. So in that, how to avoid the interference which is transmitted from the transmitter to the users. So we'll see how CDMA use code different codes for different users, and it is a orthogonal codes which helps in combating the interference. So before that, we will see the two more other things like frequency division multiple access. So the problem in frequency division multiple access in FDMA. In frequency division multiple access, the bandwidth is allotted to a particular user. So let's suppose this is the frequency, and a particular bandwidth is allocated to user 0, and then this is allocated to user 1, user 2. So in this, the resource were divided into the multiple users, and they can transmit, they can receive and transmit at the same time. So there was a each user cannot access the complete bandwidth, so the data rate and spectral efficiency was less in this FDMA. But advantage was that all users can do communication at the same time. One more technology is TDMA, so time division multiple access. So this FDMA like was used in 1G cellular communication. So this was for the FDMA used in the 1G cellular communication. The second one is TDMA, that was mostly used in the 2G cellular communication. In this, the entire bandwidth is given to each user, but for a different time slot. So let's suppose for a first time interval t, user 1 will use the entire bandwidth. Then for the next time slot t, user 1 cannot use, user 0 cannot use, user 1 will use, and so on. So the complete bandwidth is allocated to each user, but for different time slot. So that's why it is known as time division multiple access, and it was used in 2G cellular communication. But the disadvantage in FDMA was that that each user was not assigned with all bandwidth. So it reduces the data speed, data rate, and spectral efficiency. And the disadvantage with TDMA was that a user cannot communicate every time. Like it can communicate for a time slot t, and then it have to wait for the other users which will communicate for their time slots. So for solving all this issue, CDMA came in the 3G wireless technology. So this was basically used in the 3G wireless technology. For the, it was the basis for HSDPA, HSUPA, and then WCDMA and CDMA 2000. So in CDMA, like different users are multiplexed using different codes. Let's suppose a two user scenario. Consider a two user scenario. And A naught denote the symbol of the user one. That is user one. User zero we can take because A naught to user zero, and A1 denote the symbol of user one. And let the code C naught of the user, the code C naught is assigned to the user 0 is 1 comma 1 comma 1 comma 1, and code C1 is assigned to user 1 is 1 comma minus 1 comma minus 1 comma 1. So here the code length of the code is 4. So here n is equal to 4 chips, and each element of the code is also termed as a chip. So n is equal to 4. So 4 length code. So that is also known as 4 chips. Now the transmitted signal x naught of the user 0 is then given by multiplying the code C naught with the symbol A naught. Let's suppose x naught is transmitted to user 0. So x naught will be A naught into C naught. So we will get x naught as A naught comma A naught comma A naught comma A naught. Similarly, let's suppose x1 is transmitted to user 1. So x1 is equal to A1 C1. So the symbol multiplied with the code of the user 1. So we will get A1 minus A1 minus A1 comma A1. So now the transmitted signal x is equal to x naught plus x1. So x will be our a naught plus a1 comma a naught minus a1 comma a naught minus a1 comma a naught plus a1. So this is our x. Now this signal x is transmitted on the downlink from the base station to the receiver. Now the user like 0 and user 1 have to detect their own signal. So user 0 and user 1 have to extract their own signal which is transmitted from the base station. So how they will do? So like they can multiply the transmitted signal x with their codes. So the user 0 will detect the signal by let's suppose a naught plus a1 and this will be multiplied with the code of user 0, that is c0. So after that here c0 is 1 comma 1 comma 1 comma 1. So let's take the dot product. So then we will get a naught plus a1. It will get multiplied. So it's not like a dot product. Multiply and we have to sum it. So the first a naught plus a1, second one is a naught minus a1. So this is the transmitted symbol by the base station. So it will be multiplied with the codes and it will be then added. So we will get a naught plus a1 plus a naught minus a1 plus a naught minus a1 plus a naught plus a1. So the final value after adding all this a1 and a1 get cancelled. We'll get 4a naught. So actually this is the symbol that is denoted for the user 0. So user 0 recovered its symbol, that is a naught. It is just the k into the symbol. K is some constant. So similarly user 1 will detect its own signal, that is x multiplied with the code of the user 1. The code of the user 1 is 1 minus 1 minus 1 and 1. So this will be a naught plus a1 minus a naught plus a1 minus a naught plus a1 and plus a naught plus a1. So now we will get that is equal to 4a1. So this is again k into symbol of user 1. So in this way like it is just proportional to the transmitted symbol A1 for the user 1. So in this way, both user 0 and user 1 detect their own signal. So the basic properties of CDMA is the user of the different signals are multiplexed over the common wireless channel employing different codes. So now we can see like we'll see the properties of the CDMA codes. The first property is it is orthogonal. So the correlation R12 is the correlation between the code C1 and comma C2. So R12 will be summation of C0 K into C1 K, and value of K will be from 0 to 3. So in the earlier example we have codes 1 comma 1 into 1 plus 1 into minus 1 plus 1 into minus 1 and plus 1 into 1. So this will turn to 0. So, so this is the orthogonal spreading, we can say, as the summation is 0. So this correlation between the code is 0, and this in fact can be also called as orthogonal. So this helps us recover the symbols of the different users from the composite signal. So this is one of the key property of the codes employed in the CDMA wireless system. So the codes are orthogonal to each other. Now let's suppose like the symbol A naught for the user 0 have a the symbol rate of the, let's suppose, symbol rate of user 0 is 1 kilobit per second, and so the time period will be 1 by 1 kilobit per second. So it will be 10 to the power of minus 3 second, that is equal to 1 millisecond. So, and the bandwidth is 1 by t, that is 1 kilohertz. But Now the symbol A naught is multiplied with the corresponding code. So now A naught is multiplied with C naught. So it is becoming A naught, comma A naught, comma A naught, comma A naught. Thus, for each symbol A naught, one has to transmit 4 bits, 4 chips. So, like for each symbol, A naught, one has to transmit 4 chips. So, the time period will decrease by 4 and the bandwidth will increase by 4 times. So, the time period of each chips will be 1 by 4 of t. So, that is equal to 0.25 millisecond. And the bandwidth of CDMA is equal to 1 by Tc, that is equal to 4 kilohertz. So it is just a spreading of the original signal bandwidth, and hence this is also termed as the spreading code. And like it occupies a large bandwidth, so CDMA systems are also termed spread spectrum or wideband systems. Like here you can see what is spread spectrum communication. So in this, the first the symbol A naught has bandwidth of 1 kilohertz, but the CDMA spread the bandwidth by 4 times because the code used was 4 chips, so it became 4 kilohertz. So this is wideband spectrum. And this is the narrowband signal. So now there can be different orthogonal spreading codes. So like different orthogonal spreading codes can be like this: 1 1 1 1. C1 is equal to, let's suppose, 1 minus 1 minus 1 1. C2 is equal to 1 minus 1 1 and minus 1. C3 is equal to 1 1 minus 1 minus 1. So all these codes are like Rij is equal to Cik into Cjk. You can take any of this I or j from 0 to 3. This will become 0. So this is just the because all the codes are orthogonal to each other. So in CDMA, there is a parallel transmission of n symbols over n codes, and having the time interval of n into Tc. So here you can see like n codes in CDMA are transmitted over n symbols. Now in the lecture also it has been taught about the PN sequences. So we'll go through the concepts of PN sequences as well, like spreading codes based on pseudo noise sequences. So let's consider the code C2, that is 1 minus 1 1 minus 1. So this is just the random sequence of plus or minus 1. So or it is also can be termed as a pseudo noise sequence. But actually it is not a noise sequence. It is it is just a method to generate the orthogonal codes for spread spectrum, like long spreading codes based on the pseudo noise sequences. So so this can be done using a linear feedback shift register. So in the shift register, there will be a feedback, so that's why it is termed as a linear feedback shift register. We will see how linear feedback shift register is used for pseudo noise sequence generator. So linear feedback shift register for generating pseudo noise sequences. So in the linear feedback shift register, there will be a delay unit. Let's suppose this is our output. This is our output. And this is our input. And there is a feedback. Feedback is from output to input. And this feedback is an XOR of feedback of third delay unit and the final output unit. Let's suppose this is our xi. So this is our xi minus 1, xi minus 2, and xi minus 3. And output will be xi minus 4. So xi becomes xi minus 1 at the next time instant, and similarly xi minus 2 and xi minus 3 are shifted to the right, as like we can see here how the code is shifted. Let's suppose we start with the code, let's take an example, like we take a code 0000, or we take a let's start with 1111. So what will be here xi in this case? Xi will be the XOR of xi minus 3 and xi minus 4. So let's suppose this is our xi minus 4, xi minus 3, or we can take the here. So when the x all are 1, so we are doing XOR of xi minus 3 to xi minus 4. So we will get, we can write in the sequential order. So here XOR of xi minus 3 is with xi minus 4 is equal to xi. So this will become 0 because XOR of 0 0 is 0, XOR of 0 1 is 1, 1 0 is 1, and 1 1 is 0. So now in the next unit, this xi is 0 here. So in the next unit, the delayed symbol will go to xi minus 1. So now this 0 will come here, and this will go to xi minus 2. So this will become 1. Like this will go here, and xi will go to xi minus 1, and xi minus 1 will go to xi minus 2 like this. And then xi is the XOR of xi minus 3 to xi minus 4. So xi minus 1 became 0. This will become 1. This will become 1. Again this will become 1. And XOR of this is again 0. The same we can do like this. So this will become 0 0 1 1, again 0. So 0 0 0 1, and the XOR of 0 and 1 is 1. So this time 1 0 0 0, and XOR of 0 0 is 0. So like this it will go up to the 15 state. So it will go total 15 states. So that is 2 to the power of 4 minus 1. So this is our output xi minus 4, and for n is equal to 4, the total state it can go is, like maximum state it can go to 16, but through LFSR it goes 15 states. So we can also write all those states, but we can leave here. So linear feedback shift register can be like through 15 states. That is 2 to the power of 4 minus 1. And maximum number of state it can reach is for d is equal to 4, or is 2 to the power of 4, that is equal to 16. But LFSR can seen to go through all the possible state except one, which is the 0 0 0 0, or all the 0 state. In that case, like when we keep 0 0 0 0, Like if LFSR is initialized with 0000 state, it continue in the same state. So if LFSR initialized with 0,0,0,0, then like this is our xi minus 1. So in the next state again it will become 0,0,0,0,0, and it will repeat itself. So the LFSR never gets out of all the 0 states here in this case. That's why it is not initialized with all zeros. Now there are three properties of PN sequences. First is the balanced property. So in the balanced property, let's suppose a BPSK modulated PN sequence like as shown in the previously. So the PN sequence like it can generate up to maximal length of 15 states, and the total number of 1 and minus 1 in these states will be almost equal. Like in the 15 states there are 8 minus 1 and 7 plus 1 here. Like the output state, if we generate this output state, so we will get the PN sequence is equal to 1 1 1 1 0 0 0 1 0 0 as taught in this lecture. We'll get the PN sequence in this manner. So now consider this as a BPSK and map 1 with symbol minus 1 and map 0 with symbol plus 1. So our new PN sequence will become 1 is minus 1, so minus 1 minus 1 minus 1 minus 1, 0 is 1, 1 1 1 minus 1 1 1 minus 1 minus 1 1 minus 1 1. So here you can see 4 minus 1 3 1 so let's take it with different color. So there are total 8 minus 1 and 7 1. So like if the D is very large, in that case probability of xi is equal to minus 1 is nearly equal to probability of xi is equal to plus 1, that is equal to half. So this property is known as the balance property. the number of minus 1 is nearly equal to the plus 1. The second property is run length property. In run length property, a run is defined as a string of continuous values. Like, so this is the run of minus 1. So the total number of runs here is, this is the first run, second run, third run. Let's take the example here, minus 1, minus 1, minus 1, minus 1, 1, 1, 1, minus 1, 1, 1, minus 1, 1, minus 1, 1. So in this is our first run. Like it is a continuous string. So continuous value, a string of continuous value. So this is known as a string of continuous value. So here third run, fourth, fifth. Now there is only one, so sixth, seventh, and this is the eighth run. So here you can see the first run is a run of length 4. So this is known as run of length 4. Similarly, this is the run of length 3, and this is run of length 1. This is run of length 2. So now we can come to a equation. We can write as run of length n is equal to like first, see, so there is 2 runs of length 2. So 4 runs of length 1. So runs of length 1 is equal to 4. Run of length 2 is equal to, how many is the run of length 2? This is 1. There is 2. Run of length 3, is equal to 1. So the formula comes here like 1 by 8 into total runs are of length 3. we can write the common formula. Run of length n is equal to 1 by 2n of total number of runs. So just we can directly multiply it. So we'll get now run of length 1 is equal to how much? 1 by 2 into total run is 8. So we will get 3. My pencil got discharged, so let's wait for a minute. There is one mistake here, like in the above figure, that's why calculation was coming wrong. So there is only 14 sequences, 1 2 3 4 5 6 7 8 9 10 11 12 13 14. So it should be 15. So we have missed writing 1. After 1 1 there is a 2 minus 1. So here it will be 2 minus 1. So this is our run of length 2, that is the fifth run. So now run of length n. So run of length 1 is equal to 1 by 2 to the power of 1 into total number of runs, that is 8. So this will become 4. Okay. Run of length 2 is equal to 1 by 2 to the power of 2 into total number of runs. So that is equal to 8 by 4, 2. And run of length 3 is equal to 1 by 2 to the power of 3 into 8. So that is equal to 1. So we can find like this. Now coming to the third property. Sorry. So that is the autocorrelation property. So the correlation property is one of the most important properties of these PN sequences. Like let's consider again the BPSK chip sequence, how it is given, like the same chip sequence here. We can directly copy. There are 4 minus 1, 3 1, and minus 1, 2 1, minus 1, minus 1, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 and 15. So this is the BPSK chip sequence. So let's denote it by C of n. So this denoted by C of n. Now let us take the correlation properties of this sequence. Consider R like correlation of this CON with itself. So ROO 0, the correlation of sequence C naught with itself. So this is correlation of sequence 0 with itself. So this formula is summation C naught n into C naught n, and I is equal to 0 to n minus 1. So 1 by n. So this will become, sorry, 1 by n is here. So this C naught into C naught of n, like every time, like it's just a squaring, so it will add 1 plus 1 plus 1 plus 1 n times. Okay. So 1 plus 1 plus up to n times. So this will become n by n. So this is 1. Now let's suppose a circular shift version of PN sequence is there. And shift by 2 units. So C naught of n minus 2. So this will become the shifting the chip by 2 units. So our minus 1, this will come first, and this will come as a second here, shifted by 2 units, right? So minus 1 comma 1 comma minus 1 comma minus 1 comma minus 1. So this is our complete PN sequence. So now let's suppose correlation of this sequence by shifting of 2 units will be C naught n into C naught of n minus 2. So here n is 15. So we can multiply all this, like minus 1 into minus 1, then plus 1 into, sorry, this is minus 1 into 1, C naught n, then again minus 1 into minus 1, so on. So the final we will get, like after doing all this summation, is minus 1 by 15. This is equal to minus 1 by n. So the correlation of PN sequences by shifting n naught unit so this will become 1 if n naught is equal to 0 and minus 1 by n otherwise. So with this, like we have seen the auto correlation of this PN sequences. So we can plot a graph. It will become, let's suppose this is our minus 1 by n. So this is the plot of auto correlation of PN sequences, and this is 1. So these are the some of the concepts we studied today. So today we will just finish the lecture here only. So in the last week I have solved many questions related to the week 5. So now the next lecture will take on next Tuesday, that will be on the week 6th. Thank you everyone for attending.